Tomorrow, my last two lectures will be a change of pace from what we've been doing, in the sense that we've been discussing things connected with orthogonal polynomials, and tomorrow's lectures will involve Chebyshev polynomials, which have already appeared in passing, but we're going to say a lot more about them. But there are close connections between the two, which is, so the two reasons I decided to talk about is there are close connections, and second of all, Christensen, Zinchenko, and I have done some, I think, interesting work that I couldn't resist talking about. Today's lecture really has, the last lecture today is going to deal with two different, oops, I didn't turn it on? Today's lecture, this lecture, has two purposes. One is, which we will definitely use very heavily in the remaining, in the two lectures tomorrow, is the realization of Widom of what form Zago's theorem needs to take in these finite gap cases. What I will call the Widom surmise. The second and very impressionistic part of the, so when one wants to actually analyze these general almost periodic finite gap situations, there is a set of tools that's exceedingly useful for bookkeeping, for keeping straight the structure that's underlying in the Widom surmise. It was originally presented by Soden and Uditsky, and then developed by Peresdorfer and Uditsky. And I'm just going to scratch the surface to give you some of the beautiful underlying mathematics, but I'm not going to go into the technical details, which I'll tell you where you can find them. Same references. So I want to begin by reminding you about what we called Zago asymptotics. We did it for suitable measures on the unit circle. We also had a result for a single interval. So we showed that the corresponding orthogonal polynomials multiplied by z to the minus n converge to a limit. This is what was known as Zago asymptotics. So it wasn't just that the nth root of the absolute value looked like absolutes converged to absolute z. You actually had this very sharp Zago asymptotics. And for minus 2, 2, we actually proved, I didn't state it that way, that if I take the nth polynomial of z, I multiply by this object to the minus n power, it also converges to a limit. That's what's known as Zago asymptotics. We actually wrote it this way. So this is what I described when I had a theorem on the slides that said what Zago asymptotics was. But if you set z plus z inverse equal to z naught, and you solve for z in terms of z naught, well, notation got changed, unfortunately, but in any event. So right here we use the Joukowsky map. It's this Riemann map, and this occurs because it's the inverse of the Joukowsky map. Now, when e is minus 2, 2, the absolute value of this function b of z was exactly the exponential of the Green's function. We understood that when I discussed potential theory. We saw in general the rate of that one could understand where this funny b came from. Its absolute value was actually the exponential of the Green's function. That was related to regularity. Now, suppose we have a finite gap set, and we want to consider what zago-asymptotics might mean. So for some analytic function, we want to consider b to the n of z times b of z to the minus n. What do we want b of z to be? Well, we already know that if the underlying measures are going to be regular, absolute value, the nth root, is going to converge to the exponential of the Green's function. So this function b had better have absolute value equal to the exponential of g. Now that's actually very promising. G is harmonic, so we know that the phase of b should just be associated with the harmonic conjugate of the Green's function. But here there's a small problem. In the case of the unit circle, where we're looking at the exterior of the disk union infinity, in the case of minus 2, 2, where we're looking at the exterior of the disk of the interval plus infinity, the sets we're looking at are simply connected. Since they're simply connected, there's a single valued harmonic conjugate to this harmonic function. But when we take this general, and we can, for the harmonic conjugate, we can analytically continue that along any curve, but there's no reason to expect, since the set is not simply connected, that when we loop around a piece of the set E, that the phase will be what we started with. Indeed, it's an easy calculation that if you loop around a subset of this compact set, the phase will change by 2 pi I times the harmonic measure of E1. Keeping in mind this formula that the imaginary part of the harmonic conjugate is connected with the harmonic measure, different meanings of harmonic in this case. So we cannot expect B to be a single-valued analytic function. It's going to be a multi-valued analytic function, but it's going to be more than your standard multi-valued analytic function. It's going to be one whose phase only changes. The absolute value is single-valued because it's given by the Green's function. So when I go around any closed loop, everything just changes by a phase. If you think about it, what that's telling me is that there is a character of the fundamental group of the Riemann sphere, infinity included, E removed. I look at its fundamental group, and there's a group homomorphism from the fundamental group associated with any curve. There's a complex number of magnitude 1, and just by how it's defined, it's clearly has this group homomorphism property. So such a function is called character automorphic. In the cases that we've considered so far, of course, the things are simply connected, so the character is 1. So a function like this b of z is called character automorphic. In the case where E is an L-gap set, the family of possible characters is an L-dimensional torus. Typically, the characters of the characters associated with the powers of B, which means taking the character of B and looking at its images under taking powers, typically that's dense in the torus. It's not always true, but it's useful to think in those terms. It will be true if and only if the L you take L of these L plus 1 intervals, you look at or you look at all the L plus 1, they sum up to 1, so there are L distinct points. If those are all rationally independent, in fact, this will be dense in the torus. So it's a useful way to think about what these things are. So as we change n, b of z to the n changes. If I expect p to the n times b of z to the n to have a limit, that can't really happen, because as I vary n, the character, this function is a polynomial. It's analytic on the whole surface. This one has a non-trivial character, so I can't expect it to have a limit. And Whittam said, oh, what I should expect is there are a family of functions, each of which is character automorphic, that depend continuously on the underlying character. And so if chi n is the character of b to the z to the minus n, then this difference goes to 0. Which, if you think about it, this is in general because this is now a continuous function on an orbit of a rotation, irrational rotation on a torus. This is for fixed z, this is an almost periodic function. So the Zago asymptotics, which says things approach a constant, says instead they're asymptotically almost periodic. Of course, it's more with almost periods given by la-di-da-di-da. But that was his idea. The right replacement for Zago asymptotics should be in this form. And he didn't merely guess this, he actually proved he considered generally orthogonal polynomials for very nice measures concentrated on a finite number of Jordan arcs and Jordan curves. A Jordan arc is a one-to-one map of closed 0 infinity. A Jordan curve is one where gamma of 0 and gamma of 1 are equal, and the curve is analytic even at the joining point, so it's closed arcs. If it's closed, curves mean closed, arcs mean. And he proved in certain cases, we're going to talk more about this next time, both for orthogonal polynomials, but also for certain Chebyshev polynomials. He proved that you had this kind of Zago asymptotics when the measure was nice enough. Now, it turns out for further development, it's much more useful to talk about functions on the universal cover rather than multi-valued functions. It's the same thing. And this picture, which you may have seen sitting there, we will see is intimately related to this way of doing things. This is sometimes called the Fuchsian group approach, and the rest of this lecture will give you an introduction to some of the ideas underlying this approach. It's for finite gap problems and even some infinite gap problems. It's due to Soden and Uditsky, and it was developed to get Zago asymptotics by Peresdorfer, Uditsky, and it was extended and explicated in a series of papers I wrote with Christensen and Zinchenko. I mumbled, I'm here focusing on the finite gap case. They have results in infinite gap, and there is a series of papers by Christensen also discussing this point of view. For the details, you can either look in their papers, in our papers, or there are 2 chapters in the Zago theorem book that prove Zago asymptotics for certain finite gap Jacobi situations. So I'm going to explain, I'm going to want to keep the picture up there, but I'm going to explain this picture, which looks strange. It looks clearly a very attractive picture, It was drawn, by the way, in maple, and it wasn't drawn by drawing, it was drawn by writing down the right equations. Christensen did the calculation, it's from our paper. And we're going to see this is connected with one of the simplest imaginable problems, namely 3 bands and 2 gaps. May not be obvious, but we'll see eventually. And we're going to explain this picture. So let's look at some of its features. I keep this up here because I want to keep referring to it. So notice in the picture there's this faint circle. That's the boundary of the unit disk. There are all these other circles drawn. They're all orthocircles. That is, they intersect the disk orthogonally. That, if you look closely, you can believe that, but it's an important feature. There's actually, besides all these orthocircles, there's another orthocircle in the picture. Namely, the real axis is also, right? We know in the complex plane, straight lines are also circles, and this is an example of a circle which is orthogonal to the unit circle. The circles orthogonal to the unit circle, the straight lines orthogonal to the unit circle are exactly those which go through the origin. Now, these orthocircles arise from one point of view because they're in fact geodesics in the hyperbolic metric. Okay? Now, or rather, what I'm interested in is the part of the circle inside the units. I'm going to be interested in the whole circle, but the geodesic is the part of these orthocircles inside the disk. Although you can also put a hyperbolic metric on the outside, but they're nested in each other. They clearly come in generations, and indeed the true picture should have infinitely many circles. I've actually drawn only 3 generations of the circles in this picture. So there are the 4 big circles of generation 1. Inside each big circle are 3 next size circles, that's generation 2. Inside those are 3 even smaller circles, that's generation 3. And it should go on indefinitely. And I said there the straight line minus 1, 1 is also... So this picture's a little misleading, because you look at this picture and you say, oh, there are big circles and little circles. But of course, from the hyperbolic point of view, everything's equivalent. There is a Mobius transformation, a fractional linear transformation takes the disk to itself, that takes any of these orthocircles into minus 1, 1. There's no such meaning from the hyperbolic point of view to bigger circles and little circles. I've taken a fixed picture because in some sense, the disk represents a circle at infinity, and I've wanted to draw it in this Euclidean-like metric, but underlying is the more fundamental Poincaré metric. So that's what I just said. Okay. So if L is bigger than 1, this is not simply connected, and we want to lift functions to its universal cover. So what is the universal cover of this set? Well, there's a very deep theorem in complex analysis called the uniformization theorem. It's not usually stated this way. It's usually stated that the only 3 simply connected Riemann surfaces are the sphere, the plane, and the disk. But another way of stating it, if you think about universal covers, is the universal cover of any Riemann surface is the disk with a few exceptions. The only exceptions of Riemann surfaces for which the universal cover is not the disk is the Riemann sphere, the complex plane, a torus. In that case, the universal cover is the complex plane. The punctured disk, again, and that's it. Those are the only examples of Riemann surfaces whose universal cover is not the disk. Okay? And the reason really is because, as I told you, there are only these three simply connected surfaces. Riemann surfaces have a group of deck transformations. The deck transformations are always discrete groups of automorphisms that have no fixed points. The Riemann sphere has no such maps, so the only Riemann surface that has the Riemann sphere as its universal cover is the Riemann sphere. The complex plane, the only fixed point free automorphisms are in fact affine maps, not affine maps, translations. Affine maps have fixed points if they're not translations. So the only are translations. The only discrete subgroups of translations are the integers and two-dimensional lattice. That gives you the tori and this. Of course, I say a torus. There is not a single torus from the point of view of complex analysis. There's a complicated set of them associated with elliptic functions. So we know in our case there is a map x of z from the disk onto this set, which is many to one and is a covering map. Right? This disk is up there. It's a universal cover. Each point corresponds to some fiber. That fiber is going to be many to one because this is not simply connected. As with any covering map, there's a discrete group of transformations which preserves the complex structure. They're Mobius transformations. So there's a discrete group of Mobius transformations, and these were dubbed by Poincaré Fuchsian groups, something that really annoyed Klein to no end. And that's why when he talked about the non-disk case, he decided to call them Kleinian groups. There was this tremendous competition between Klein, who was already very well established, and this almost unknown mathematician named Poincaré in France, and Klein drove himself so hard that he had a nervous breakdown afterwards, and in some sense never returned to doing mathematics at the level that he'd done. And there was a lot of hard feeling between the Germans and the French over this. Anyhow, this underlying group of transformations the deck transformations mean that if I apply one of these maps to something up here, it gives me another point that projects down to the same point. So this map X, which is the projection down from D to this set, is left invariant by the group of Mobius transformations. And indeed, if you think about it, the fact that the deck transformations act transitively on the inverse image of any point tells you that 2 points in the disk have the same image downstairs if and only if there's a point in the Fuchsian group with that property. Now I want you to notice that this map X is not unique. if I take any such map and I compose it with any Mobius transform, any invertible Mobius, so it means any Mobius transformation, this will also be it has all the properties of the covering map. Of course, the Fuchsian group won't be gamma anymore. It will be G inverse gamma G. We can normalize X. We can pick it uniquely. So this is just like on ordinary Riemann maps. There's more than one Riemann map from a simply connected surface into the disk. In order to fix the map, you have to decide what point is going into 0. Or if I want to go in the other direction from the disk, I have to decide what point 0 goes into and what the derivative is, the phase of the derivative is. So I can normalize the map by demanding that the point 0 in the disk gets mapped to the point infinity on the Riemann surface with E removed, and that the residue of the corresponding pole is positive. This is like determining a Riemann map by demanding that the origin go into some given point and the derivative of the function be positive there. This, if you think about it, this condition actually tells you that it maps the region above the real line, into the part into the lower half plane in the Dirichlet domain of gamma. So what happens is, right, in the disk I take any point and there are its images under the Fuchsian group. I want to pick out, more or less, a unique point on each orbit and put them together to get a natural fundamental domain. The Dirichlet domain is defined in terms of the Poincaré metric on the disk to be those points which are closest to 0 among the entire orbit. So I take a point W and I look at all the images of 0 under the Fuchsian group, and I want those points which are closest to 0. So in this picture, it will turn out the region that is that has these 4 pieces of the unit circle, these inside the unit circle and inside the complements, or outside these circles, is going to be this Dirichlet domain. Now, the interior of the domain, this does not pick out a unique point in every orbit. The interior of the domain does pick out a unique point, but won't be all points. That's actually the region inside. The Dirichlet domain is just the closure. So what I defined as D super 0, super degree, whatever you want to call it, is the interior of this set, and this is the closure. They're fundamental domains for X in the sense that X is 1, 1 on the inside. It's 2 to 1 on the extra points. The 2 complex conjugate points, if I take any point in the boundary here, it and a point, corresponding point, it's not complex conjugate, corresponding point over there will go into the same point. So if I, it's actually a point there. If I look at this point, there's going to be another point in the orbit on that circle. So it's 2 to 1 on the circles, and otherwise 1 to 1. And it's basically a fundamental domain. And if I wanted to get a true fundamental domain, I just take the pieces that are in the upper half plane. It will turn out that the image of the interior will be this full domain with the gaps filled in, and that x will be 1, 1 there, and these correspond, these points will all map into the gaps of our finite gap set. So, okay, so by normalization, the function x of z goes like c over z near infinity. So near z equals 0, as z runs from 0 down to -1, this point's going to infinity. The map is monotone as I go from infinity, from 0 down, there's a minus sign there. So the map, as I decrease z, make z more and more negative, the corresponding function x of z is monotone increasing. So this piece of the real axis gets mapped down to the part of the real axis that goes from -infinity up to the lowest point, alpha 1. Why alpha 1? Because as I go up the axis, when I reach alpha 1, I'm actually reaching the boundary of my Riemann surface, which is exactly this disk. If I, instead of hitting alpha 1, go slightly above the gap, so the band, I'm hitting the first band. If I go slightly above the first band, then I scoot just below here, I go in that direction. If I go below the first band, then I'm going in the lower half plane maps into the upper half disk, I'm scooting along there. So as I go along here, that corresponds to part of the infinite gap. And then if I scoot along there, I'm going along a band. Similarly, if I go in the other direction, right, if I go from here up to there, I'm going from infinity down to beta L plus 1. So really, the interval from -1, 1 is mapped into the infinite, quote, infinite gap, the two pieces of the semi-infinite. Now, once I go above the first gap, so I scoot along here, I reach a gap in the set. That's not at the edge, that has to be inside my domain. So as I now go back along the gap, I'm going to trace out some curve in the disk. What do I know about that curve? Well, I could have normalized the map, so instead of sending infinity to 0, instead of sending 0 to infinity, I could take 0, send it into the middle of this new gap, the gap from beta 1 to alpha 2. If I do that, then it's easy to see that the real axis will map into that gap. But those two maps are related by a Mobius transformation. So this set has to be the image under a Mobius transformation of -1, 1. That is, it has to be an orthocircle. So these orthocircles correspond to gaps. They come in complex conjugate pairs depending on whether I've gone above or below the bands in each place. And this picture corresponds to 3 gaps, this gap, and two gaps, 2 finite gaps plus the infinite gap, and 3 bands. The 3 bands correspond to this piece, and that piece, and their complex conjugates, which are the above and below the bands. So we can understand part of this figure. As I said, we have two gaps and 3 bands, and we understand why the fundamental domain is what it is. Or at least why this is a fundamental domain. Why it's the Dirichlet is not quite clear yet, although it isn't hard to prove. In general, if we had L gaps, the disk would have 2 L disjoint orthocircles removed, up in the upper half, L in the upper half plane, and their L conjugates. Each orthocircle in the upper half plane corresponds to a distinct gap. Now, let's consider for a second 2 different conjugate linear maps. Let's first of all consider the complex conjugation, and let's let Rj be reflection in the jth orthocircle in the upper half plane. That is, if that orthocircle is given by this formula, this is what I mean by the reflection. Absolutely standard formula for complex reflection. Each of these maps is a conjugate Mobius transformation, and Rj takes infinity into Zj, obviously. Rj leaves the jth orthocircle pointwise fixed. Take a product of Rj and C. X is real on -1, 1. It obeys, therefore, X of Z obeys this map. So X is real on the orthocircle associated with Rj, because we saw this orthocircle gets mapped into a gap on the real axis. So it also obeys this property, which means the product of Rj and C leaves X invariant. It's one of the elements of Fuchsian group. It's not hard to prove. We know this Fuchsian group is, right, it's associated with the abelianization of the fundamental group of this set. That's exactly a torus of dimension L. So the corresponding group, which is dual to it, has L generators. As I run through the L orthocircles, these run through a set of generators of the Fuchsian group. So the Fuchsian group, if we return to our example, is associated to, the maps are, you first reflect in the real axis and then reflect in one of the orthocircles. If we do that, right, what happens to the boundary of this domain? This orthocircle, I first complex conjugate, that brings me here. Then I reflect in this circle, that brings me to that circle. If I start out here, when I reflect, I wind up there and then I stay fixed. So this circle goes into the big circle, but the other 3 circles get mapped into 3 circles inside. The same thing is true for each of these pictures. One of the 4 circles gets mapped into its complex conjugate, because it first complex conjugates and then it's fixed. And the other 3 get mapped into small circles. So the second generation of circles is exactly what you see here. The next time I reflect, I get smaller circles ad nauseum. The orbits under this group are infinite. The groups, the the group generated by the gammas is in fact the fundamental group, and it's not hard to see that it's a free group on some number of generators. And so it's a very complicated non-abelian group that this Fuchsian group generates, and the corresponding orbits have 1 point, unless I take an orbit that actually is on one of the ortho circles. The corresponding orbits have 1 point in each of these circles that you see there. The set of limit points is called lambda, and pictorially it's obviously nowhere dense. The circles are getting smaller and smaller. So the set of limit points is a subset of the disk. So by limit points, I literally mean the closure of an orbit. I take 0, I look at the orbit, I look at its limit points, which, because the group is discrete, there are no limit points inside the disk, but there will, of course, be limit points on the disk. And it's easy to see it's nowhere dense. And we'll see in a moment, not I'll prove it, but I'll state a theorem, it actually has Hausdorff dimensions strictly less than 1. And it's not hard to see that if I avoid these limit points, right, I remind you, this map X is real on this little piece of axis. This corresponds exactly to points on the bands. So by the Schwartz reflection principle, the map X, which was originally defined on the disk, actually has an analytic continuation to the outside of the disk. And it's not hard to see it's analytic in the entire complex plane except for this set of limit points. And this map, if I imagine the inside of the disk going into the upper sheet of my Riemann surface, and the outside going into the reflected points going into the lower points, this is actually a covering map of the corresponding Riemann surface associated with the finite gap set. However, it's not the universal cover because this set lambda has been taken out, but it's still a covering map. As I said, when I said analytic, it's in fact a meromorphic continuation because all the reflected images of the orbit of 0, no, actually they go to, well, we know 0, it's not analytic at 0, it's got a pole there, it's got lots of poles inside the disk. Okay, so I talked about the covering map. There's an important theorem that Bearden, who is actually retired now but a Cambridge professor, proved 45 years ago roughly, that certain finitely generated Fuchsian groups, including the ones associated to finite gap sets, have a number of properties. He was able to analyze those Fuchsian groups, and it has the following consequences. The set of limit points actually has Hausdorff dimensions strictly less than 1. Secondly, if I let Rk be the union of the interiors of all the circles at generation k, so if you count up the number of circles, right, at generation 1, there are 2L circles. At generation 2, in each of the 2L circles, there are 2L minus 1 circles. At generation k, the number of circles is 2L times 2L minus 1 to the k minus 1. The total, if I look at these circles and look at their Lebesgue measure of their intersection with the unit disk, this size decays exponentially. Again, if you look at the picture, it's certainly believable that this is exponential, although there is a playoff here that makes it not quite trivial. The number of orthocircles is growing exponentially. Their sizes are clearly decreasing individual, that this decrease in size beats out the growth of the number of circles is a deep theorem, and it's really what Bearden proved. And it's not true in general for Fuchsian groups that happen to have nowhere dense. There do exist Fuchsian groups with nowhere dense limit sets for which this decrease is not exponential. And he could prove there's something called the Poincare exponent. He was able to prove if I take any point z and I look at its images under the Fuchsian group, that it obeys this Blaschke-like condition, even for an S less than 1, and therefore in particular it does for S equals 1. Since this is true, we can form a Blaschke product. So B of z is the Blaschke product. I take Blaschke factors at each of the zeros. Let's take the orbit through z. I'm going to take the zero that I'm going to look at the orbit associated with 0. For each point on that orbit, I take the corresponding Blaschke factor, take the product of all those by this condition that converges, and I'm going to call it B for Blaschke product. I want to emphasize it's different from the B that the lecture began with. It's different from the B that I started with. Indeed, we made it, after I prepared the slides, we made a decision for the paper. What I called B at the beginning of this lecture, we're going to call B inverse, because we called this B in our earliest set of papers. They're inverses of one another. One is a map, right? The B I started the lecture with was of magnitude bigger than 1. This Blaschke product is less than 1. They're essentially inverses of one another. This is defined on D and not on the complement of E, but there is a relation. If this is the set of Blaschkes associated with the orbit through Z0, then these have the same zeros and poles, so the ratio of these two B's is a constant. That is these product of Z's is actually a character automorphic function. Its log defines a function here that's harmonic on that set that goes to 0 as one approaches E, because approaching the set E corresponds to associating the boundary of the disk. And so it has the right logarithmic singularity as you approach Z0. It's a potential theorist Green's function. In particular, the Blaschke product associated with 0 is exactly the exponential of minus the Green's function, its absolute value. So this is a way of making very explicit the phases. This is where I'm going to stop. This is only the beginning of the analysis. This is the first set of tools you need to discuss to further analyze the finite gap set, but it's a very beautiful set of tools. I couldn't resist, even though I can't show you how the tools work, introducing them to you and letting you understand why this picture really is a piece of finite gap spectral analysis. Thank you.
Are there any questions?
Yeah.
Say, Miss, now has this Widom surmise been proven or not?
Sometimes. So Widom proved it in general for these analytic curves, closed curves. As I said, it's sometimes, more or less, Widom has it for nice enough things in the case of orthogonal polynomials, but only he did not consider point masses outside. If you want to consider point masses outside, there's this natural Blaschke condition which you can write down, and there is a full Zago type theorem, which, if you will, is verifying the Widom surmise for orthogonal polynomials where you have exactly the analog of the conditions I wrote down in the single interval case, namely you need a Blaschke condition on the roots and a little bit more. That was essentially the first version of that was in the paper of Peresdorfer and Uditsky, although they didn't have as much information. They didn't have the Blaschke condition on the zeros. They had a second note later where they filled that in, and there's a general discussion of this in the papers with Christensen and Zinchenko. And one of the things we did is actually construct examples where you get Zago asymptotics but do not get but do not have a Zago condition. What one gets as the asymptotics of the polynomials is actually quite interesting. So what actually happens in this case is if you have one of these things where the measure obeys a Zago condition, then in fact the corresponding Jacobi matrix is asymptotic to a point on the isospectral torus. So it's not moving towards a fixed point on the torus, because the torus itself, as you translate, moves along an orbit. It's moving towards a single orbit, and it converges to that point. And one version of Zago asymptotics is that the ratio of the polynomials for this non-isospectral torus element divided by the polynomials for the corresponding point on the torus actually converges to a limit. But the limit is only almost periodic, but if you will, this actually proves even more than the Widom surmise. So for the finite gap case, the Widom surmise on the real axis, the Widom surmise has been proven even with these point masses outside. For Chebyshev polynomials, Widom proved the Widom surmise for closed curves, but only conjectured it for there's a subtlety, and that's exactly what the subject of the next two lectures are. One of the things I will discuss in the last lecture is how one gets the Widom surmise for Chebyshev polynomials. For infinite gap, it's a whole new story. Sometimes it can be done, sometimes you need conditions. So we're going to see something called the Paro-Widom condition rear its head, and it will come up. And the interesting thing is it's the same Widom in Paro-Widom and Widom surmise, but Widom introduced this in a totally different context, and I don't think realized Widom had anything to do with what goes on in the infinite gap case. But Widom is a really incredibly deep mathematician.
Question. So here, the disk was seen as a universal covering of the complement of finitely many intervals on the real line. But is there something similar if you have arcs, finitely many arcs on the unit circle?
Any Riemann surface
Yeah, right.
that isn't one of these special ones has the disk as its cover.
Yeah, no, that I understand. But but then you
So there's always a
went on,
covering
for
map.
instance, right? But then you could also take sets which are not intervals.
You could take sets which are not intervals. You could take.
Probably these things.
So you don't. So this picture depends very heavily on the complex conjugate symmetry. And if your set doesn't have the complex conjugate symmetry, then you won't have quite such a pretty looking picture. But there's still some underlying Fuchsian group.
So, but the arcs on the unit circle do have such a complex conjugation structure just because the circle can be mapped to the real line.
So there are subsets, there are arcs. No. What's the question?
So, I mean, the disk was the covering of the set, which
Right.
was
Right.
the complement of
Right.
finitely many intervals on the real.
Right.
So the fact that these were intervals and were on the real line had some role in the discussion.
Right.
The question is whether if these intervals are instead arcs on the unit circle, it's the same thing.
So there is some mumbling in our papers, all our papers, that the same techniques should extend to OPUC because in that case there's a very similar picture. And I seem to remember that in one of our papers we may have done a little bit of the general theory, but I don't think anyone has yet written down the details in that case. But I have no doubt there are some extra complications. See, one thing that's important here is in the real line case, your group is equal to sort of, you don't have a piece of the group associated with the set in your infinity. When you do it for the disk, the dimensions, there's an extra factor that actually makes the analysis more complicated. So I discussed this in detail in my OPUC book, not the Fuchsian group thing, but the issues when you try to analyze the periodic case, there's an extra complication. Those same complications would occur. So the answer to your question is, I think anyone who's worked on these things, and that's not a large number of people, is sure you can do this also for OPUC. But I don't know anyone who's actually written out the details. Maybe Peter does, but I don't know anyone who's written out the details for OPUC. Do you know anyone who's done the Zago analysis for finite gap on OPUC?
I'm not exactly sure, but that's, I don't want to. It seems we don't finish with respect to orthogonal polynomial he did.
So yeah. If there are no points outside, if you don't have the extra point masses, Widom essentially already did this for any number, orthogonal polynomials for any number of they don't have to be in the unit circle. But once you put the masses in, you probably need more machinery, and it should be that this extends to OPUC. In particular, right, there are results here that have to do with the asymptotics of the Jacobi or Vrblonsky parameters. In the general case, Widom doesn't talk about that, so it's not the you can't talk about isospectral torus in quite the same way, but But I think there are, I think there are results, but again, I don't think anyone's worked it out for OPUC with some extra point masses. That's not in Woodham.
Before going on the coffee break, I think we can thank again